Good afternoon, everyone. We're going to start with our afternoon talks. First of all, I'll just thank you to the organizers organizing this and making this happen. This is a great place for it. It's personally my first time to Silomar, so love it here. Thank you so much. Okay, so Cuauhtémoc Sáenz-Romero from the University of Michoacan is going to tell us about a fur that's endemic to Mexico and some population dynamics with it.
So, Abies religiosa, sacred fir, is what created forest where overwintering the monarch butterflies that migrate from northeast United States to Mexico. Is the same species, but not the same population that the ones that come very near of here at the sanctuary that is very close. And they go to a very, very specific site in the neovolcanic axis, which is a mountain chain with very high altitude. And we have this monarch butterfly biosphere reserve, where you can see this very spectacular aggregation of monarchs. The problem is climatic change, among other problems, because inside the monarch butterfly biosphere reserve, climatic niche modeling indicate clearly that the suitable climatic habitat for the sacred fir is going to disappear completely by the end of the century, even when I think our reserve is more or less successful because ecotourism provides an income for the local people that put them away of the logging. So we have, I think, a success case of conservation, but now conservation in situ looks that it's not enough. And what are the, sorry, what happened? I don't know, it's moving by itself. What are our management options? Our option will be to move from the monarch butterfly reserve to places at higher altitude like Nevado de Toluca, which is 4,700 meters. The summits here are 3,500. And we have established, and I like the comment of Brad Sinclair of the importance of the reciprocal transplants, because we put a transplant at low altitude, 2,600 meters, and we could see the future. And when see the future, I mean, we have a reference site at 3,000 meters, moving from 3,000 to 2,600 is 400 meters, which is equivalent to 2 degrees. And we could see what happened with 2 degrees, a massive mortality of the seedlings. Here is just the beginning of the experiment. What we have now, 6% of survival with 2 degrees more and 19% less precipitation than our reference site. So it's really a tragedy what may happen. And we can see that at low altitude, what will happen. We have constructed this zonification based on common garden tests, measuring how many meters of altitudinal difference makes two populations genetically different in quantitative traits, based on methodology developed by Jerry Reffeld at Moscow, Idaho, who inspired in his work. And it's why we have this 350 meters of width of the altitudinal band. So our suggestion for management is collect seed here, produce seedlings in the north and move to the next one. Not only because the width is 350 meters, also because to shift the climate for 2030 at higher altitude to compensate about 1.5 degrees. It is relatively easy to say that, but to especially at high altitude is a different history because it's complicated. Go to the field and do it. The problem here is we cannot move from some tree to somewhere inside the monarch butterfly because the summits are right there. So we have to change of mountain to another volcano. This is a previous experiment of assisted migration inside the natural distribution of the species, and we found the extremely importance of use shrubs as north plants. So a plant that provides shade and decrease the variation of temperature, either high temperatures at the middle day, because at 3,000 meters there's a lot of insolation, and at night temperatures below zero. So the oscillation of the temperature decrease a lot under the shade of these roofs. Is what we call it protected assisted migration. Migration because we're moving the provenances, assisted because require the human intervention, and protection because we need these roofs as Norse plants. And the difference is huge. So we have more than 90% of survival under the shade and only 5% of survival out of the shade. So it's a very delicate stage of this species, the seedlings. So they die very easily. So we decided to go to Nevado de Toluca, which is outside of the reserve, and we established 4 provenance tests. From provenances collected along an altitudinal gradient in a way that we could test how much we can move to higher altitude to expand the upper limit of the species. The upper limit of the species, 3,500 meters. And this is our reference site, 3,400. And we have one at 4,000 meters, which is the timberline. So we wanted to see in an extreme situation how we'll do this species. So the preliminary results after 1 year of planting, which is the more critical year for the seedlings, is this one. So for every 1 degree that we move to colder place, we have about 5% of mortality. The mortality is kind of messy for several reasons, but it's more clear if we see a stress index, which is based on the appearance of the seedlings that we have test this system. Is very simple to do it. So green, dark color looks like healthy seedlings, and brownish, yellowish seedlings is a stress seedling, and we have an index with 6 points. And you can see how moving to a colder side, the seedlings are more stressful. This feeling that I have is that is making very stressed the seedlings is a combination of what Jerry Redfield might call a climate without contemporary analogs, meaning a climate that doesn't exist today, or it didn't exist in historical climate, meaning at night, still at 3,500 meters, 4,000 meters are very low temperatures, below zero, 5, 6, 7, 8 below 0 Celsius. But what is new, that is usual, but what is new is that winter and spring are now very dry. So the total amount of precipitation has not changed much, but the distribution of the precipitation has changed a lot. So rainy season is more violent, at night it's more violent the rain, but the dry season, cold in winter and warmer in spring, is much more dry. That makes this combination of temperatures below 0 at night and very dry make the season very special. So we are hanging on there, and we will see what happens. Thank you very much.
I think we have time for a few questions.
I really make an effort to use only 8 minutes, so I really appreciate you.
Yeah, no, you were spot on. I have a question. So how much gene flow do you think there is occurring between the bottom to the top of the mountains?
I think there is a very strong gene flow. There are measurements of that, not mine or other colleagues of human, but the pressure of the selection by the temperature is so strong that we have shown in previous common tests that there is a strong genetic differentiation in response to the mean temperature of the coldest month. And it's about 350 meters that made of the altitudinal difference that made two populations genetically different for quantitative traits, such as drought resistance and elongation of the shoot. So despite the gene flow, there is a lot of selection pressure due to temperature. Right.
You looked at the relationship with mean annual temperature. Did you try other variables or multiple variables to try to account for what you just described?
Not yet, but we will do that. What happens is actually we have data from 11 months, and we're waiting for more data to explore Usually, another graph that works very well to understand what is going on is the annual dryness index. So degree days squared divided by mean annual temperature. That is very powerful to understand what is going on.
Yeah, thanks. Thank you.
Thank you.